Welcome to the third video. For this video, I'll be explaining acid bases, and so let's briefly go over the key terms of acid bases. So the Bronsted-Lowry definition of an acid is a proton donor, and bases are proton acceptors. And this is just, protons are in OChem are referring to hydrogens without any electrons. And also the Lewis definition is acids are electron acceptors. So we can classify them as electrophiles. And bases are electron donors or nucleophiles. So moving on, the basic structure of any acid-base reaction is an acid plus a base, and forming an acid or I should say sort of like this. So what is happening is in curved arrows, using curved arrows, the base is pulling off a hydrogen and leaving the electrons behind, so that this HB means that it's the conjugate acid because it gained a proton, and this A right here just means a conjugate base. So this is like the most basic pathway of an acid-base reaction, and so here's an example of one. So with sodium hydroxide becomes, and so what we have to do is first identify the acid and bases. If you've done a lot of practice with that functional groups, you'll automatically identify that this CO2H is a carboxylic group. So one thing we need to do is, everyone needs to do when learning organic chemistry is to memorize some of the basic functional group pKa's, so that you can quickly identify which is an acid and which is a base. And so for carboxylic groups, they have a pKa of 3 to 5. So automatically this NaOH will be our base. So I'll just mark them as acid bases. And the other way to identify them is by understanding that NaOH is a Na plus and OH minus, where it's an ionic bond. So it's ionic, so that it forms a kind of a fake bond, just an attraction to the negative charge. And so from the definition, it says that for Lewis or we can go up and see that Bronsted-Lowry says that bases are proton acceptors, so that kind of matches, the definition matches the basic path of acid-base reactions, while the Lewis acid or base is saying that the base is an electron donor or nucleophiles. And so what nucleophiles mean is that they have an abundance of electrons, so they would try to pull a proton or in some way try to neutralize their charge. So then we can observe that we see that the OH minus just means that oxygen has a lot of electrons to share, so it can share it with a hydrogen. So let's first draw out the structure, and that's what I typically like to do. So this will be our CH3, CH2 carboxylic acid plus Na plus, and for the sake of clarity, I'll show all the electrons. So using curved arrows, we know that, so the base basically is a proton acceptor, so it pulls the hydrogen off, leaving behind the electrons. So I'll shrink this and draw the result, which is, or actually let's move to the next page and draw the result. And the result will be the oxygen gaining a minus charge plus a H2O, water forming, because 2 hydrogens with an oxygen is water. So from here, well, you might ask, well, where is sodium then? Sodium sort of floats near, or is attracted to the negative charge, so it will float near the negatively charged oxygen in the carboxylic acid's conjugate base. So this is our, this is our conjugate base, and this is our conjugate acid. Now, at the final step, what we need to do, which is the most important part, is to see if will this reaction actually occur. Now, what we do is we look at the acids on both sides, and determine their pKa values. Look at their pKa values, so 3 to 5. pKa of water, which is also something that you need to know, is 15.74. So anything above 15.74 pKa is considered a weak acid, and anything below is considered a strong acid. Now we'll get into that in a second, but so what will happen right here is that the pKa goes from low to high. And that is important because then this reaction will actually go. So low to high, so a mnemonic that helps remember this is low to high, fly, fly, fly. High to low, no, no, no. That's an easy way to understand or remember when checking if the reaction will actually go. And so now finally, solvents are used for acid-base reactions to help them sort of mix together and collide together more easily. It's sort of like mixing sugar so that or salt in water so that it'll dissolve. But so what will happen is a lot of people get tricked or tripped up by solvents. One key thing to note is that the base and solvents have to have similar pKs. So what I mean by that is, if we have, let's say, NaOH as our base, if we use a solvent that is let's say NH3, now then NH3 or ammonium liquid is about 38 pKa. Now our base is conjugate acid, so H2O. By adding a proton, we can look at its conjugate acid. So H2O's pKa is about 15.74. So the solvent and the reagent, the base, will react. So we don't want that. So we don't want this. And now cross it out like that. So we don't want this. So what will happen, what we'll use normally is if we have NaOH, we'll just put it under water so that it will be in equilibrium. So I hope this clears up the solvent confusion that occurs in a lot of people. Now, let's go to the stability of acids and comparing between similar acids and figuring out the more acidic acid or more acidic molecule. So a mnemonic that we use is I here. And so the first letter of I here is I, which means inductive effect, or stands for inductive effect. So inductive effect just means that if there is any electronegative atom nearby the acid, so let's say we have a OH group right here, or a carboxylic group, anything, the electronegative atom that is near this will help pull the density of the electron clouds or electron density away from the hydrogen, so that it is exposed to make the base deprotonate much easier. So naturally, when we're comparing, two carboxylic acids, let's say, but one has a chlorine versus one has a fluorine, we know that this molecule is more acidic because fluorine is more electronegative than chlorine, so it'll pull harder on the electron density. Now, when we're looking at the or when we're comparing between two different acids, let's say we were comparing carboxylic acid versus let's say a OH minus group, or actually HI or HCl. Let's just use HCl for example. So the pKa of HCl is -7, and pKa of CO2H is 3 to 5. So naturally, when we're comparing these two acids, we can directly compare pKa values and say that, okay, so HCl is more acidic than carboxylic acid. But then how do we use pKa values in when comparing bases when bases don't have pKa values? So one way, a way we do this is by comparing their conjugate acids' pK values. So the conjugate acid of OH is H2O by adding a proton, and its pK value is 15.74. Now NH2 is NH3 as its conjugate acid by adding a proton, and its pK value is 38. And so what we know is that the higher the pKa, the weaker the acid, but stronger the base. So this high pK is saying that NH3 is a weak acid, but its base is going to be very strong. So a high pK value of a conjugate acid indicates that the base will be strong. And so then we can conclude that the NH2 is a stronger base. So I hope that clears up comparing bases and comparing acids. And so the next letter from I here is H. So what does H stand for? H stands for hybridization. So hybridization. So what does that have to do with anything. So when we're comparing carbons to each other, sp3, we understand that it's a single carbon, or a single bonded carbons, and it will have hydrogens attached to it. So what we can see is that these hydrogens over here, let me use a different color. These hydrogens over here actually are equal distance or equal distance as the bond between the carbons. So what that means is that it is much harder for the bases to pull. It's harder. So, and we can also see that from the pK value having 50 for an alkane. And so what about an sp2 carbon? So carbons and hydrogens, carbon double bonded and hydrogens. Now this actually increases the acidity because the double bond in the middle kind of shortens the length, and so while the hydrogen and carbon bonds remain long. So that makes bases actually deprotonate much easier, and we can see that it is more acidic because it has a pK of 44 for an sp2 carbon. Now for an sp carbon, it is even more acidic because it has shorter length between the carbons. And so one way I think about it is that the carbons are only paying attention to each other, and kind of their attention is drawn away from the hydrogen. And so this makes it even more acidic because it's easier to deprotonate it. And we can also see that in the pK values, and the pK values kind of match it by showing that it is 25. And even through energy diagrams, we can observe that it is more, as P character increases, the stability, so the energy is higher, meaning that stability is decreasing. Because p orbitals are at a higher energy level. So more p percent character, the less stable it is. So that concludes the hybridization. And so the next letter is from I here is E. And that is electronegativity. So electronegativity. So electronegativity. So when we're looking at electronegativity, the more electronegative it is of a carbon, or not a carbon but an atom attached to the hydrogen that we're looking at, the more acidic it is, like we said earlier. So when we're looking at this hydrogen right here, this oxygen is very electronegative, hence why the electron cloud that's surrounding it is kind of away from the hydrogen because of the oxygen pulling away. So that's why electronegativity is important regarding acids. And so one other example is HF versus, or HF versus carboxylic acid. Now, one of the reasons is that reasons why HF is more acidic is because of this electronegativity of fluorine, because fluorine is the most electronegative. And that's why electronegativity is important when looking at stability or acidity of acids. So the next letter in the I here, mnemonic, is A. And that stands for atomic size. So atomic size, what does that have to do with anything? So atomic size comes into play when we're comparing HI versus HCl. So electronegativity between these two acids are about the same because they are in the same group of halogens, but there's a size difference where iodine is bigger than chlorine. Now, why is that important? Because they are both equally or about equally electronegative. The size allows iodine to store more or hold more electrons. So its pull, while its pull is strong, its ability to hold in the electrons allows even it to be more acidic because it holds more electrons, exposing the hydrogen. Now then, the final letter in I here is resonance. So resonance, right here, resonance. So resonance comes into play when we're looking at, or is directly correlated to the stability, and that's why it's more acidic, because it can atoms or molecules that have more resonance structures can move the electron density and store it. So it's kind of similar to the atomic size in I here. So when we're comparing two two molecules, OH or carboxylic acid versus carbon or a alcohol group. So what we do, or why resonance comes into play, is we look at the conjugate base of each molecule. And so carboxylic acid, when you deprotonate it, has this negatively charged oxygen. Now what it can do is it can move the electrons, forming a pi bond, and then push over this pi bond electrons, forming another resonance structure that almost looks identical. Now, so then we got two resonance structures for carboxylic acid. Then let's look at the conjugate base of alcohol. And what we can see is that there is no way for it to move its electrons, because then carbon would have 5 bonds. And so we can't do that. So it does not have resonance. Hence why carboxylic acid is more acidic. And this is an explanation of why the pKa values of pKa of carboxylic is 3 to 5, and pKa of alcohols is around 16 to 18. This is like an explanation as to why there is a difference in pKa. So I hope that helps with acid bases. I hope that you do many problems regarding acid bases so that you can get used to it, because acid bases base concepts are a key foundation in being successful in organic chemistry.